Hello guys, welcome to another video. In this video I'll discuss about the design of an isolated footing. We have a question over here. For an isolated reinforced concrete footing has to transfer a load of 800 kN from a square column of 300 into 300. This is in mm. Consider concrete grade of M20 and Tutor steel and sole bearing capacity of 180 kN per meter square. So this concrete grade and steel grade is for both, that is for isolated footing as well as the column. And design an isolated footing and draw a neat footing sketch showing all the reinforcement. So starting here with the step number 1, that is to calculate the area required for footing. Here we have formula 1.1 times of the load divided by bearing capacity of the soil. So this P is the unfactored load. Make sure it is the unfactored load, and 1.1 times this is the addition of 10%. So this 10% is added for the self weight of footing. This is the load coming from the column, and we have to consider 10%, that is the self weight of the footing. Now substitute the value 1.1 times of 800 divided by 180. This comes as 4.88 meter square. Now assuming a square footing, you can assume as a rectangular footing or a square footing. For now I am considering a square footing because I have a square column. So that means B is equal to L. Then area is equal to L into B. So substituting L is equal to B, then we get B square is equal to A, and for area we have under root 4.88. This comes as 2.21 meter. So nearly taking this value as 3 meter. Now adapting 3 meter into 3 meter square footing. So we have got the dimension of a square footing. The step number 2 is to calculate the pressure under footing. Okay, if this is a footing, okay, then it will be subjected to a pressure from this soil. So we have to calculate this, which is W. Then we have formula for it. W is equal to Pu by A, this is ultimate load, plus Mu by Z, this is moment, and Z is section modulus. For our question we are not provided with any moment, so we are not taking it. So Mu is equal to 0, not given in the question. If it was given, then we have to substitute. It will be a plus minus over here. Okay, now substitute the value of load. So it is ultimate load, so it has to be multiplied by the partial safety factor, that is 1.5. 1.5 times of 800. Don't include the self weight of the footing. Okay, we are just considering the load. Now we get this as 133.33 kilonewton per meter square. Area is 3 into 3 for the footing. So we get the pressure under footing. Step number 2 is done. Step number 3, calculation of bending moment, one-way shear and two-way shear. So this is the section of the footing and this is the plan of the footing. Okay, just understand this figure. So this is the footing section and this is the plan. This is the column of 300 mm dimension, so 0.3. okay, 3 meter by 3 meter is the size of the footing, and as I said, it is subjected to a pressure from the soil, which is W, and it is equal to 133.33 kilonewton per meter square, and is a UDL, uniformly distributed load. It may be a uniformly varying load also depending on the condition, but for now it is a uniformly distributed load. If there was a moment in this case, then it would have been a uniformly varying load, because we have plus minus sign over there, and considering the moment we get two values at two ends. Okay, at this and at this end, Mu minimum or Mu max as you consider at either side. So there will be a uniformly varying load. For now it is a uniformly distributed load. Now we have to calculate the bending moment, and for a UDL, okay, of length L, the bending moment can be calculated by a formula, which is bending moment is equal to W into L by 2. Now let us calculate the bending moment in this case, and for bending moment we will consider the weight per unit length. So W into 1, W into length, okay, as I said in the above formula. And for bending moment, okay, the critical section from the face of the column is at the edge. Okay, so we'll consider the length up to that portion. So this is the length that is to be considered for calculating the bending moment. And if this is the total length, this is the total length of the footing, that is 3 meter, L we can say, and this is the Coulomb. So small l is for the Coulomb, length of Coulomb. Got it? L minus L divided by 2. So we'll get this. L minus L is this much length, okay, and divided by 2 we'll get 1 of this. So critical section for bending moment is this portion. So L into L divided by 2. I hope you get it this. Okay, this is the length. This is the length. So this much UDL, okay, from here to here, and the bending moment W into L divided by half, okay, centroidal distance. So W into L divided by 2. So this is divided by 2. Substitute the value of W, which is 133.33 into 1. So this is simply 1. Now substitute the length of the footing, 3 minus 0.3 divided by 2, length of the Coulomb 0.3 into 1 by 2, 3 minus 0.3 by 2. So this comes as 121.496 kilonewton meter. So this is the maximum bending moment acting in this Coulomb, acting in this footing. Then from this moment we can find out the depth required. Okay, so as you can see here, for Fe415 mx is equal to 0.138 FCK BD square. So this is simply we have moment is equal to 0.36 FCK B into D minus 0.42 XU. Now the value of XU can be converted into terms of D in terms for the Fe415. Then we get mx is equal to 0.138 FCK BD square. So this is the expression we get by substituting the value of XU. Now substitute the value of mx, that is 121.496, converting it into Newton mm, we get 121.496 into 10 to the power 6, 0.138 FCK is 20, B is equal to 1000 because we consider a meter, 1 meter of section as in this slab, into D required square. Okay, so this is, from this we can get the depth required. So we get D required as 209.81 mm. Okay, so this depth is necessary to resist the bending moment acting in the footing. Okay, but the footing is subjected to one-way shear and two-way shear as well, so for which the greater depth is necessary. So this depth may not be enough to resist the one-way shear and two-way shear, so we adopt a value twice than that of the calculated one. So as I said, adopting D is equal to 500 mm because taking twice of the calculated value to withstand or to resist the one-way shear and two-way shear. We will check whether this depth is sufficient or not, but for now taking 500, taking a cover of 50 mm, then overall depth of the footing is 550 mm. Okay, now to check for the one-way shear. Okay, before that let me calculate one-way shear. Critical section for one-way shear occurs at D distance. Okay, so D is the depth. Okay, higher the value, greater the distance or critical section from the face of the Coulomb. So it is necessary to take a greater value of D to resist the one-way shear effect. Okay, so as I said here in the figure, critical section for one way at a distance D from the face of the Coulomb at either side, and for the shear force for a UDL is equal to V is equal to W into L minus D. Again it is a weight per unit length into L minus L by 2 minus D. Now substitute the value correspondingly, then we get Vmax is equal to 113.33 kilonewton. Similarly, tau max is equal to Vmax by BD. This is the shear stress, maximum shear stress. Vmax by BD 113.33 into 10 to the power 3 Newton divided by 1000, taking a 1 meter section. So 1000 into 500. Okay, don't get confused with the overall depth. So taking effective depth, we get this value as 0.226 Newton per mm square. This is the maximum shear stress acting on the footing. Now let us check with the permissible value, okay, which is less or equal to 0.28 Newton per mm square. Okay, what does this signify is that if you go to table number 19 of IS 456 page 73, then you will find for M20 grade the minimum shear strength of concrete is 0.28. okay, so we are using M20 and the minimum shear strength of concrete is 0.28 Newton, and the value calculated with the depth as 500, the maximum shear stress acting is 0.226 Newton per mm square, which is less than the design shear strength of concrete. Hence there is no requirement of any shear reinforcement in the footing. Okay, so this is what we understand from this point. Okay, the shear strength of concrete is sufficient to withstand the shearing effect. Now similarly, let us go to the another one, that is to calculate the two-way shear, and critical section for two-way shear is at distance d by 2 from the face of column at all four sides. Okay, so you can see here d by 2, so this is d by 2. Okay, critical section for two-way shear at a distance d by 2 from all four sides. Then let us calculate the maximum shear force is equal to W into, so it is acting on all four sides, so we will go through the area, not by a distance. Okay, so W into L into B, this is the area of the footing minus area of the critical section. Now if we see here, L plus d by 2 plus d by 2, so d by 2 plus d by 2, it will be L plus d finally. Okay, similarly in this section, B plus d by 2 plus d by 2, finally we get L B plus d on all four sides. So the area of this section will be L plus d into B plus d. So what I have written here, W into L into B, area of footing, minus area of the critical section, which is L plus d into B plus d. Substitute the value. This W load is 133.33, 3 into 3 minus 0.3 plus 0.5 into 0.3 plus 0.5. D is the effective depth, so we get this value as 1114.68 kilonewton. This is the maximum two-way shear acting on the footing. Now let us find the maximum shear stress. Tau max is equal to V max by area. Now we will be taking the perimeter. Okay, this is the perimeter, 2 times of L plus D plus 2 times of L plus D. Okay, this is B here, but we have both as equal. So L plus D, L plus D, L plus D, B plus D, B plus D. So twice we have here 2 times of L plus D plus 2 times of B plus D into D. This is the depth, we are finding the area. So finally substitute the value 114, sorry, make a correction over here, this is 1114.68 and substitute other term, that is L plus D and other things, and we will get this value as 0.69 Newton per mm square. Okay, and now from clause, okay, we have to check with the maximum permissible value. So from clause 31.6.3 page 58 and 59 of IS 456, we have, for permissible shear stress, when shear reinforcement is not to be provided, the calculated shear stress at the critical section shall not exceed Ks tau c. So we will not be providing any shear reinforcement in the footing. So Ks is equal to 0.5 plus beta s, but for this the Ks should not be greater than 1, beta s being the ratio of short side to the long side of the column, and tau c is equal to 0.25 under root fck in limit state. Design shear capacity is equal to K into tau c, and K is equal to 0.5 plus beta c, and beta c is equal to 300 by 300 because we have a square column of 300 by 300 size, so this comes as 1. Okay, then finally K is equal to 0.5 plus 1, which is equal to 1.5, but the code has said this value cannot be greater than 1, so taking K as 1. Then tau c is equal to 0.25 under root fck, and take fck for the grade of concrete of the footing. So finally we get this as 1.18 Newton per mm square. Finally K into tau c, substitute the value, we get this as 1.118 Newton per mm square, which is greater than that of the value of the stress acting on the footing. That is, maximum shear stress on the footing is less than that of the permissible stress, hence it is okay. So we finally conclude that the depth we have provided for the footing is sufficient to resist the bending moment, one-way shear and two-way shear. Now let's go to another step to calculate the area of reinforcement. Mx is equal to 0.87 FYAST into D 1 minus FYAST by FCK into BD. So this is from the Annex G of IS 456 and this is for the under reinforced section. Okay. Now let's substitute the value. Mx 128.496 kilonewton meter into 10 to the power 6, converting into Newton mm, and substituting other terms. We are interested to find AST. So 415. The depth is 500. We are considering a section of 1000 mm, and finally we get 692.99 mm square as the area of a steel. This much steel has to be provided. Now let's check whether this steel considers the minimum area steel requirement. So we have 0.12% of BD from the code. BD is the gross area considering the depth. Okay, 0.12 by 100 into 1000 into 500. So this value comes as 660 mm square. Okay, make sure to take the overall depth. Make a correction over here, it is the overall depth. Now let us find the spacing. Adopting a bar size of 16 mm, okay, then spacing is equal to width of the section divided by area of steel provided to the area of individual bar. Okay, providing 16 mm bar, we get area of steel of individual bar as 201.06. Width of the section is 1000 mm divided by area of steel provided 692.99. This comes as 290.17 mm, and according to the code the spacing should be at least less than that of 300 mm or should be less or equal to 3 times of the effective depth. So one is 300 and another is 1500 mm, providing a 16 mm diameter bar at 200 mm center to center. So this spacing satisfies both of these conditions, so it is okay. Now let us go to the development length required for the footing. Length required for transferring the stress from the steel to the concrete is known as development length, and in this figure the length measured from the face of the column, that is LD, is the development length. To accommodate the development length, you can find in page number 42 of IS 456, and development length we can find LD is equal to pi sigma s divided by 4 into tau BD. Now substituting the terms, phi is the bar size, 16 into 0.87 times of 415. Okay, this is the stress in the bar considered at design load, that is 87% of yield stress of the bar, 4 into tau BD. So tau BD, the value of tau BD, that is design bone stress, is 1.2 for M20 grade. This is also from the code, you can find at page number 43, and 1.6 because according to the code for deformed bar this value can be increased by 60%, so it is multiplied by 1.6, that is the design bone stress can be multiplied by 1.6, that is can be increased by 60%. This value comes as 752.18 mm, and the available length, the length of the bar available at the footing. Okay, so 3 minus 0.3. Why? Let me show you. This is 3 meter and this section is 0.3. okay, and we have also provided a 50 mm cover, and the bar comes like this of the column. So the available length of bar, this is the cover, 3 minus 0.3 divided by 2, this means we have reduced the cover which is of 0.50 mm, that is 0.05. okay, so this comes as 1.3 meter. So this is the available length to accommodate the development length. So the available length is greater than LD, so it is okay. We didn't consider this cover because it can be bent over here. Okay, so the development length is also satisfied. Step 7, bearing stress on column. Okay, this is also calculated from the code. We have a formula for this. Bearing stress on column is equal to 1.5 times of dead load plus live load divided by area of column. This dead load is unfactored load and we have no live load acting on the column. 1.5 times of 800, area of column 300 into 300. Okay, and finally we get 13.33 Newton per mm square. Make sure to convert this into the required unit. Now bearing capacity of concrete, this was the stress. Now bearing capacity of concrete, under root A1 by A2 into 0.45 FCK. This is from the code at page number 65, 34.4 clause. Okay, so A1 by A2 and into 0.45 FCK. So what is A1 and A2? Okay, and make sure this FCK is for footing. Okay, A1 is the supporting area for bearing of footing, and A2 is the loaded area of at the column base. Okay, so that means A2 is for column and A1 is for the footing. Now A2, as I said, for column it is 300 into 300, so this comes as 90,000 mm square. But for A1, A2 means this area. This is the supporting area for bearing of footing. See, we have this slope as 1:2. Okay, let us take this slope as 1:2. Then the depth here being 500, then 500 into 2 plus 300 plus 500 into 2, so this comes as 2300. So on either side, okay, on either side it will be 2300, 2300. So then A1 by A2, we get this value as 7.67, and the code has said the bearing pressure on the loaded area shall not exceed the permissible bearing stress in direct compression multiplied by a value equal to this, but not greater than 2. So this value cannot be greater than 2. So taking this value as 2, finally bearing capacity of concrete is equal to 2, this is A1 by A2 into FCK to 0.45. Okay, so substitute this value FCK and then we get 18 Newton per mm square. Okay, this is the bearing capacity of concrete, and bearing stress on column is 13.33. So it is also okay. So in this way the design procedure of a isolated footing is completed. This is the reinforcement detailing. Okay, this is the column, okay, of size 0.3 meter, and we have 16 mm diameter bar at 200 mm center to center spacing, 3 meter. This is also 3 meter. Okay, this is the effective depth 500 mm, and this is the development length of the column. Thank you.